Good afternoon, everybody. Are you there? Are you able to see my screen? Great. So how are you doing, everybody? Aren't you glad this is the last lecture of the whole semester? Don't you feel good? You know, I am fine, thank you, Cindy. I just can't wait for this semester to finish. Just 1 week to go. And actually today, it's not going to be too bad. You just have one more report due tomorrow. And then next week, I will go over the common mistakes. I will take questions, etc. And we're done. Okay? Oh. Final exam? Yes, I'm preparing for it. I know you're tired. We're all tired. Okay? Didn't I tell you? I think I'm lucky because my children are big. I mean, they're all working now, and I don't have small children at home. I can imagine. Yeah, I can imagine those instructors having small children at home during this time. It is just too much. It's just too much to handle because we're changing our system in the middle of the semester. Okay, that is hard. Okay. But anyway, just one more week and we're done. Okay. I hope everybody here is on. Okay, so I have 14 students on board. Okay, my plan today is to go over some common mistakes on the Esther report. I finished grading during the weekend, and I think there are a couple points. I think students have the knowledge, but they didn't really write down the answers correctly. So yeah, so I want to touch up a little bit. On top of that, I need to finish the ALDOL chapter. Okay, today I'm not going to talk much about the reaction. Instead, I need to give you some flavor about the spectroscopy UV range. Okay, we will provide molecules some ultraviolet photons and get something excited, and then we can pick up some signals and we can characterize product based on the properties that will come out of this UV spectroscopy. Okay, and then later on I will probably go walk through the questions with you in the back. And also there is one important issue here because quite a few instructors already wrote to me about the lab notebook. Okay, they asked me, do I want to collect all the notebook from all of you? And I can tell you during this stage, I think it will be super, super difficult to collect your lab notebook. Imagine each student's already built the lab book, like with how many pages writing in the book, in the notebook. I think easy, like 20, 30 pages. And then for you to scan every page and then for the instructors to go through every single page, that is probably too much. However, I did announce the policy to all instructors, okay? We will collect your notebook in case you are on borderline. Okay, that is to say, when we finish the final exam and then we realize the grade you collected during the semester is right at the border of passing, no passing, or at the borderline of A, B, or BC, etc., we will ask you to submit your notebook through the Dropbox. Okay, so only students on the borderline cases will be asked to submit the notebook. Okay, is that good? Is that good news? So you want to make sure you're not on the border. Okay, and the other thing is, I always emphasize this during this semester when I teach my students in the lab. The notebook you built for this course is actually a great resume when you do a job interview, when you are you're being considered as a good candidate for a job opening, and that your interviewer probably makes some comments about, hey, I think your credentials not gonna be too impressive because I have MIT students or Berkeley or Caltech students interviewing for the same job. But at least you can show the interviewer, I don't have a good publication yet at my age. However, you can find my work habit in this notebook, okay, in my lab notebook, and I'm willing to submit it and then show the interviewer. I can tell you this strategy actually worked for many of my students, okay? It worked, okay? So I want to share with you, okay? Not all of you will be in the same situation, but I'm just telling you, it so happened that my advice worked in some occasions, okay? And the other thing is, I don't know whether you have a question. Okay, let me check how many students are actually on board now. Oh, we have 16 students. Okay, I think I can get going now, okay? I want to start our lecture today by showing you the common mistakes. All right, now let me read your question, okay? Hold on. Thank you for responding so quickly. Okay, now, so who wrote to me? Benjamin, yes, I remember you talking about in class. Yeah, thank you. Benjamin has been paying attention to my remarks quite often. And okay, and so are you all ready now? Okay, let me go over the Esther reports a little bit, okay? Okay, please always stop me if you have a question, okay? All right. Okay. Okay, writing down balance equation for ester reaction of your product. And okay, watch out. Some people don't even know you actually assigned to do a product. Okay, it is based on your last name. Okay, so not everybody gave me the perfect answer, especially when it comes down to catalyst writing. This catalyst usually placed on top of the arrows. And you know this is a two-way, like reversible reaction, okay? Forward reaction with one arrow pointing to the right, and the reverse reaction pointing to the left, okay? And the catalyst is sulfuric acid in the ester experiment. I hope you still remember. So where do you put your catalyst? You want to put the catalyst on top of the arrow pointing to the right, okay? Because the catalyst is being regenerated, it's not consumed. It is not part of the reactant structure, it's not part of the product structure either. And therefore, okay, you want it on top of the arrow. Okay, so when people look at the reaction, they know the key changes. Okay, catalyst is regenerated without getting changed. Okay, so we're not going to incorporate that in the reactant side, nor on the product side. Okay, all right. So this is just common sense. I want to share with you. Okay, this reaction writing is important. Okay, let me tell you, because I write questions for the final. I know I do ask students what is the right reaction writing, okay, from the following choices. Okay, I did ask people to pick the right answer. Okay. All right, in the esterification reaction, you know the side product is water. Am I right? Okay, and so you also want to include that, and having this water indicated in the structure in the reaction rating is super important for a reversible equation, for a reversible chemical reaction. It is because when you show people, if you just like me join a chemical firm, when you start your professional life, okay, I joined BP. That was my first professional job in my whole life, okay? And in the factory, if you show production, this is a reversible reaction and the water is a byproduct. I can tell you, I guarantee those process engineers would know they will have to remove the water constantly during the reaction in order to keep the reaction going to the forward direction. Understand? Okay? It is super important you indicate that side product must be removed during the reaction. Okay? So if you say this is the byproduct is water, then they will have to do something about removing the water. They can put a drying towel. Okay, they can purge more nitrogen. Okay, they can regulate the nitrogen gas purging and rely on this purging to bring out some water droplets. Understand? And also, when you sell your product to the customer, I guarantee your product wants to know what is the content, percentage content of your product. Okay, percentage content means, hey, is this 99% pure or is this 99.99% pure? The price will be so different. Understand? Okay, if you show, yeah, I have a side product and it's supposed to be generated in 5% by weight. This is very, very, very common to ester. Okay, generating water by 5 to 10% of weight percent. So yeah, then the customer will make sure they're not paying you the money for the molecules of water you ship to them. Understand? They want you to specify, and so it means a lot to this to the sales department to negotiate the specification with customer based on how much you can remove that water. Okay, it's a big deal. That's why I emphasize the side product here in this reaction rating, especially for the reversible reaction. Okay, you know, if you leave water in there, the reaction will not go forward. It will just go reverse. Okay, then the yield never go up. You can, you can supervise that reactor for 5 hours, 10 hours, another 20 hours, and then the yield does not go up because you didn't get rid of the water, okay? So now you understand how important that is to show side product, okay? All right, next, the reaction mechanism, most people did very well. I was very surprised. I think you all did a very good job, maybe, from lecture professor's class. Okay, most people learned it. Okay, I need to rely on the sulfuric acid providing proton as a catalyst to kick off the reaction. Okay, generate a good electrophile on the carbon, okay, etc. People did very well here, okay? All right, next. This is the part I was a little bit surprised. Some people didn't know we will have to assume, you're not producing any product. However, you're supposed to do theoretical yield. This is assuming you have 100% yield, okay? Based on the moles, based on the limiting reagent calculation, are you able to show me the grams of the product, okay? I can tell you the cost, okay? The cost calculation in the real world, you know, this is part of the equation. You have that number, and then you get your actual yield, and then you can calculate the cost. Understand? Okay. And did I tell you the yield, the cost means a lot to your paycheck? Okay. We're asking you with 1 point penalty here, but in the future, if you're asked to do the theoretical yield calculation to help the company structure the cost, and you don't know how to do it, it may cost your career, okay? Because you don't know how to do it, okay? All right, so this is quite important, okay? And so also I want you to report the boiling point. And I ask everybody to look up the literature value, okay? So they're different depending on the type of alcohol you start out with, okay? So this is also, quite a few students didn't get this part looked up. They're saying, ooh, we didn't do it, so I don't have to mess around with those numbers. No, that's not true, okay? You still want to pretend for today the same. For aldol reaction, the same, okay? You will have to report, okay, the melting point, etc. You do the theoretical yield calculation again, all right? All right. All right, now most people did very well here, okay? I'm very happy with what I see. The questions in the final, yeah, oftentimes we give you something similar, okay? I will give you a molecule, okay? And I'll give you a name or maybe a structure, okay? And then I give you a couple spectra I want you to match, okay? Now the spectra, NMR spectra of the following is actually this compound. Now tell me which one, okay? Yeah, a question like this is very common in the final, understand? Okay, and did I tell you in the final exam, there will be at least seven questions on NMR, okay? At least, okay? All right, now the post-lab questions here, okay? I can tell you most of you did okay. I wouldn't say perfect, okay? Because oftentimes I ask questions to see if you understand what you're doing in the procedure. Why do we want to add sodium bicarbonate when we do the extraction of the final product? Why do we want to do that? And I want you to recall that reaction. When you produce the ester, you're using acid, alcohol, react them together in the presence of a catalyst. The catalyst is sulfuric acid, am I right? And the end product is ester and water, okay? So adding sodium bicarbonate is for you, hello, for you to get rid of all the acids, residues of acid. The extra acid you introduce as a catalyst, that sulfuric acid, of course, you don't want that in the end product, okay? And the extra acid you use in large amount, okay? That needs to be removed also. How can your customer tolerate any sulfuric acid in the end product? And by the way, we don't, okay, if you remember, we're using the glacial acetic acid as a starting material reactant also, okay? Okay, so the reaction mixture actually smells like vinegar, okay? And you're supposed to produce fruity grape fragrance at the end. the ester all smell really fruity. Okay, so why do you want that vinegar smell? I can tell you, when I check students' product, I always take a sniff, okay? And I want to see if you really got rid of the vinegar, okay? The very strong smell vinegar. It takes only a little bit, very trace amount to create a vinegar smell in that fragrance, okay? And it's very unpleasant, okay? All right, so you're adding this sodium bicarbonate to neutralize the acid, okay? So actually not many people mention this word, neutralize. Yeah, you neutralize the acid, you remove the acid is gonna stay in the aqueous layer. This is the sodium bicarbonate layer, okay? And I think I show you the photos already. There are 2 layers, okay? And the aqueous layer will be the layer that sodium bicarbonate and acid neutralize together, okay? And so couple wash by this baking soda solution will take care of it, okay? All right, is this important? Yes, again, okay? It is affecting the product quality. It's super important, all right? And we want you to include a equation for explanation. Most people did this part, okay? But the end of the equation, people gave me H2CO3, okay? That is coming from the bicarbonate and the acid put together. And you forgot, actually the carbonic acid, which is H2CO3, that compound immediately decomposed to produce CO2 and water. So you will create bubble, okay? So it is just like 7-Up, soda, Coca-Cola. Yeah, when you open the can, it is a CO2 popping out of the can, okay? And so the carbonic acid in water is just unstable. It wants to produce CO2 and water, okay? But I didn't penalize you, okay? I'm just letting you know, okay? We want this equation to help you understand there is also, you know, some indicator for you to see when the bubbles kind of disappear, okay? When you add fresh amount of sodium bicarbonate into the workup, into the reaction mixture, and you don't see the bubble anymore, it is a good indicator that all the acids are being eliminated, okay? All right, but you know, most people did well here. It is just the answer of carbonic acid, which is H2CO3. That part I didn't find it perfect, okay? All right, next. Now this is something I think you should all know, okay? Can you use sodium hydroxide instead of sodium bicarbonate in that workup? Okay, I can tell you not at all. It is because sodium hydroxide is such a strong base. And sodium bicarbonate has to be used because sodium hydroxide will decompose the ester, but sodium bicarbonate will not decompose ester, okay? Try to understand ester group, the C double bond O and then C O single bond. That ester group is not a stable functional group, okay? Let me show you right here. Can you see this clearly? Hello? Can someone respond? Hello, ladies and gentlemen. I want to make sure I'm not talking to myself, okay? Can you see the screen? Are we connected? Hello? Hello, hello?
Yeah, we're connected.
Yes, yeah, we are connected.
We're on the group chat.
Yeah.
Okay.
Thank
Thank you.
Mm-hmm.
I can tell you, it happens in one of the instructors' Zoom section. My goodness, he says, you know, his internet is actually, you know, giving trouble, creating trouble, and then for like 30 minutes, he has been talking to himself. Okay, so I need to make sure sometimes.
So sad.
Yeah, it happens. But you know, yeah, it happens. And I can tell you, because I also teach the advanced organic chemistry, the 400 level class, and there are quite a few students cannot stay connected. Okay, and I can tell you, in the advanced organic chemistry, I really have to lecture a long time. Oh, so they always wait for me to upload the YouTube video. Anyway, I'm glad that it's not happening here. Okay. All right. I want to show you the ester group. It's actually not stable group. It's not a super stable group. Okay. The reason is either base or acid can kill it. See that? Is this the ester? Yes. Look at the OH strong base. Okay, I can tell you the baking soda, sodium bicarbonate will not do this. The sodium hydroxide definitely will kill it. Okay, let me show you how it killed the molecule. Okay, with this OH minus charge, it will find this carbonyl group carbon right here. Remember, this is a partially positive carbon. Okay, are you following my arrow? Okay, this is super attracted by this. Okay, so attack. Okay, guess what? When this is being attached to this carbon, and you have this, remember the intermediate, you drew the structure, remember, you did it once. Okay, you wrote the mechanism once on the worksheet. And guess what? When this electron pair, lone pair from oxygen comes back, it will kick out the methanol group, okay? And it's actually written as methoxy minus charge, but you know, if you have any water nearby, this is a super strong base. It will take the hydrogen from water and produce alcohol at the same time. All right, so you see this is the carboxylic acid and alcohol, right? So remember, ester was created by acid and alcohol put together. Now this is being reversed, completely reversed back to the reactant because of strong base, okay? The strong acid will do the same. Acid can catalyze the hydrolysis as well, decompose, okay? And you're familiar with this, okay? Hydrogen plus will be interested in very high electron density area, okay? It will come here, and guess what? Okay, positive here. Then it will move this electron pair up, okay? At the same time, you leave a carbon plus and right here, and it will take water right away. Don't forget, when you add acid, acid is always provided in the aqueous condition. So water is always readily available from the surrounding. Okay, so when this happens, look at this. Okay, you will get rid of the methanol. Okay, at the same time, this hydrogen will donate one proton to the methoxy, and you create alcohol again at the same time, leaving the acid behind. Okay, now this plus charge will be reversed or stabilized by this this electron pair right here. Okay, so you regenerate the hydrogen plus in this process. The net result is ester decompose, ester decompose. Do you see that? Okay, so for this reason, ester is not a very super stable product. Okay, so over time, the ester will decompose. Okay, will decompose, especially when you leave the ester in the presence of any base residues or acid residues. Okay, acid or base residues will kill ester. Okay. So most people can tell me, yes, this is too strong of a base, okay? But you didn't really tell me, okay? You didn't tell me it is actually hydrolysis, okay? But I didn't penalize you, but I want you to know that. I can tell you, because this is like a common sense to chemists, and I have a feeling, yeah, maybe the lecturer professor can add one of this question in the final exam. You never know. Okay, so I can tell you this is important common sense. Okay, strong base acid residues will kill ester. Okay. All right, most people did very well here. Okay, knowing this has 6 carbon. Carboxylic acid is high boiling, okay? Because there's hydrogen bonding there, okay? So people do well here, okay? It is the last one. Now this one, a lot of people make mistake, okay? I only give the students either partial credit or you completely don't get it. Okay, I think I lecture about this, so I emphasize that for how long. I think I dwell on this particular trick of adding glacial acetic acid. We don't want aqueous acetic acid. We want glacial. Okay. Why is that? Why is that? What the reason is the glacial acetic acid is anhydrous. Okay. A lot of people say that. I really like it. Okay. But what is the problem if you introduce the non-anhydrous form? If you introduce acetic acid in aqueous form, that means you dissolve this compound in water and start the reaction. Aha. Didn't I say that at the beginning of the reaction? I told you because water is a byproduct, right? If you introduce a reactant and you introduce water at the same time, then you are pushing this reaction backwards right from the start. Am I right? Okay, I can tell you this reaction will be doomed for this low yield. Okay, it will not produce a lot of ester product because you introduce the water to start. It is all because this is a reversible reaction. Okay, having water at the starting point, when you write the reaction, you remember water is a byproduct. Okay, so even though you introduce the reactant there, okay, that water will push the reaction backwards. Okay, okay, so this is very unfortunate. And so in the factory, we never make the ester using the aqueous acid. Okay, we don't want any drop of water at all, or else you're just wasting a lot of time. Okay, you're not getting the yield. All right, it is all because of Le Chatelier principle. Le Chatelier. Okay, is everybody with me? Yeah. Thank you. Thank you. So a lot of people explain, yeah, the difference between the glacial acetic acid and the aqueous. They know the difference, but they didn't explain why we don't want the aqueous. We don't want that water because the reaction is reversible. That's why. Okay. All right. Most people did very well in here, okay? Very, very happy seeing that IR being reviewed and review again, and we all get the key function group identified. Okay, so far so good. And I think the, yeah, most people receive the points around, I'll say 16 to 18 or 15 to 18 points, okay? Yeah, so not bad. It is just a couple touch up here, okay? All right. All right, so the last chapter, ALDOL. I want all of you to review what we have done. Oh, by the way, I think I can just open this. I can just open this, okay. ALDOL chapter, according to your last name, okay, you have your own starting benzaldehyde, okay? And here, you're supposed to write a balance equation again. I want you to include blah, 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 blah. Now, I can tell you, most people screw up this part, the coefficient, okay? I'm alarming you. Okay, you will be using the benzaldehyde and acetone together, okay? 1 molecule each. Is this the right equation or not? If it is 1-to-1 ratio. Well, I want you to think about it, okay? Let me see. Now people love it. No, you're right. Lazo, you're right. Nope. Oh, nope. I want you to stay alert, okay? I'm giving you this because I'm giving you this warning because I can tell you every semester people just make mistake there, okay? Okay, let me see. Okay, hold on. Let me see if I have this. Okay, procedure. All right. Okay, now everybody, I want you to pay attention one more time. Reaction writing, okay? Is this a benzaldehyde? Yes. Okay, now the other compound here, okay, we only give you alpha hydrogen without showing what the R is, okay? But you know you have another carbon or something here when, well, you have acetone, okay? So you know each alpha hydrogen is capable of reacting with its benzaldehyde and form a CC double bond. Okay, please go back to the mechanism. I hope you still remember it, okay? And if I give you another CH3, what's gonna happen here? You can extend it, am I right? You can extend it, all right. So watch out for this coefficient, okay? Because I want you to figure out the limiting reagent later, okay? Not today, but the due date is tomorrow, okay? If I give you acetone with the amount given, according to the lab manual, are you able to figure out limiting reagent if I give you this and acetone, okay? All right, let me go back, okay? Let me go back to the lab packet. Okay. All right, I want students to pay attention right here. Now someone responded. Do we use acetophenone or acetone? The answer is acetone. You go by what our lab manual tell you, okay? You go by our own lab manual. I demonstrated the photo using acetophenone, okay? But we go by acetone and the amount is given in the lab manual, okay? Thank you. And right here, on top of this reaction, okay, pretty much standard aldol condensation, okay, we want you to pay attention to this. The pre-lab discussion on the UV spectroscopy, lambda max, and whatever that means, okay, I will show you what that is, okay? And this is a very important characteristic property associated with organic compound, quite unique, okay? Just like melting point, the melting point of, let's say, yeah, aspirin, you're probably very familiar with it, okay? Aspirin has this melting point, okay, okay, and then benzaldehyde has the melting point, okay, and you can describe the organic compound with quite a few, you know, test results, such as melting point, such as boiling point, such as refractive index, such as RF value, right? Okay, now lambda max is another one, okay? What is lambda max? Okay, the compound you made from this reaction called aldol condensation is actually capable of absorbing UV light. What does UV stand for, everybody? What does UV stand for?
Ultraviolet.
Thank you. Thank you, Nathan. It is ultraviolet, and we were talking about the application, potential application of this aldol condensation, right? Last time, students were saying, yeah, how about sunscreen? Yeah, definitely. A lot of molecules that look like aldol condensation product you make today, yeah, they're being used as a sunblock, yes, okay? They use the aldol product you make today as a building block, okay? And then they expand the size of molecule by extending more carbon-carbon bond, and then, yeah, they create huge molecules with a lot of conjugation. Aha, do you hear the word conjugation? And then when this huge big weird molecule is made, you dissolve it in ethanol, for example. Ethanol is pretty standard. When we run the test for UV spectroscopy, we dissolve your aldol compound in ethanol, and then we just put the quartz cell, okay, the like sample tube, in the light path of ultraviolet photons. And then we want to detect how much photons have been absorbed by the solution, okay? Yeah, it's very straightforward test, okay? Very similar to IR, okay? IR, you see a whole bunch of peaks, yeah. UV, you will also see a peak, okay? And I want to show you the peak later. Okay, now before I show you the peak, I want you to take a look at this molecule one more time, okay? And tell me, is this molecule conjugated? When I say conjugated, what does it mean? Hello? Can someone tell me what does it mean? Conjugate?
SP2.
Bond, double bond, double bond, single bond, double bond, single bond, double bond, single bond.
You're right. Yeah, the double bond, single bond, and it's sp2 hybridization. Okay, now Cindy, it is not only sp2 hybridization. You see this double bond, double bond, single, and then you see this inside of the 6,6H5. You know this is a phenyl group, right? Okay, it is a benzene ring right here. Is this conjugated here? You bet. Okay. Conjugation all the way from here to, oh, all the way into the ring. And then what do you want to call this? Electrons. When they're conjugated, one big feature about the electrons along this alternation of double, single, double, single, double, single, double, double, single, they are most stable. I can tell you, Cindy, this is not quite a good word for it, okay? Have you learned a word called delocalize? The electrons are delocalized. Have you learned that word?
Once.
Yes. When you have a conjugated double bond, a conjugated system, I should say, conjugated system, then you know you have a unhybridized p orbital. Okay, now you have this electron right here, one electron here. Okay, so look at the double bond right here one more time. The first bond is called sigma bond, am I right? The second bond is called the pi bond. You learned that before, have you? Yeah, okay, the same here, okay? The same goes to the aromatic ring, yes, okay? And the second bond, which is the pi bond, all come from the p orbital, the electron located in the p orbital, not coming from the sp3 hybridized or sp2 hybridized orbital. No, it is not, okay? So try to understand the electrons here, either here or here, okay, or inside the ring, okay? The double bond is not in the fixed position. They're not. They are delocalized. So when we say delocalized, what does it mean? It is not fixed here. And have you seen the expression dot, dot, dot line here, and then dot, dot, dot here? Have you seen those expressions before? Resonance, very good. Lazo, very good. All right, so that means this double bond here is also dot, 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 and dot, 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 and dot, dot, dot here. Are you following my hand? Yeah. It is not just a pure single bond. It has delocalized electron traveling through. Are you all with me? Yes. Okay. So inside this phenyl group, okay, you can draw the 6-member ring, and then you see 3 pi bond there. And those pi bond are not being fixed. They are delocalized, okay? Delocalized. Okay, so if you ask me, Miss Jean, this pi electron right here, this pi electron here, and the pi electron inside the phenyl group right here, do they know there is a boundary? Okay, delocalized. Does it mean this electron know which carbon they're from? I can tell you they don't know where they're from, okay? Originally, yes, before the bond was created, they know electron come from oxygen, the electron come from carbon, they create that pi bond. But once conjugation is being built up, then if you grab the electron here and you ask, hey, who's your mom? Who's your carbon mom? That electron will tell you, I don't know, because I travel from here, all the way here, all the way here, here, and inside the ring, across the border, across the Atlantic Ocean. Yeah, I'm enjoying myself. I'm traveling around the world, okay? That is called delocalized electron. Are y'all with me? Okay? It is true, okay? It is true. You grab any pi electron here, because it is all dot, 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 all the way into the ring. They share the same territory. They enjoy traveling. All of the pi electron enjoy the same traveling, okay? There's no travel ban. No, they have free traveling, no border. Thank you. Thank you, Aaron. You agree. It actually makes more sense to me now. Okay. Aaron, let me tell you. And Cindy, let me tell you. I think students in my 223A will know Miss Jean has been very delocalized to a very delocalized girl in my own house, okay? I can tell you, yes, I was born to this family. My mom and loved me. My dad loved me so much, so dearly, but I have this neighbor. So when I was born, okay, ever since my toddler age, I visit my neighbor, and they always give me candies or snacks in the afternoon, so I can eat my lunch here, and I can enjoy my dinner here. Okay, I may sleep with my neighboring friends. Okay, and I enjoy all my childhood this way. Okay, and when I come home, my mom always asks me, "How come you never hungry, huh?" Well, I wasn't too good with my language that time, but one time I told my mom, everybody gave me good food. Okay, when I was playing with my neighboring, friends, I can tell you this is called a very delocalized machine. Okay, that was my childhood. Okay, delocalized. Okay, so it is true here with the electron, okay? All right, now look at this. Everybody follow me, okay? If I give you a benzaldehyde and I give you, my goodness, a alpha hydrogen donor that has also conjugated system here, my goodness. Look at this molecule, okay? Is it super conjugated right here? Are you with me? Not only here, it travels across the border. Okay, cross the border. Oh my goodness, this is a huge conjugated system. Okay, this is super, super conjugated. And I can tell you, when you have a molecule like this, they have a very valuable commercial value right here. They can protect your eyes, okay? Because they want to absorb UV light. Okay? All right. You just have to follow me now, okay? And I'll show you what happened. Let me see. Look at this. Oh, yeah. I think I showed you this already. All right, let me. Okay, so acetophenone, okay, react with these. Yeah, we have some crazy molecules already made this way. I can tell you a lot of UV absorber are created by reacting benzaldehyde with these. And then we have how many phenyl group now in the molecule? You will have at least 2, and then keep going. Okay, you can add. You can continue. You can continue another aldol condensation as long as you have, a more functional group introduced into the reaction mixture, okay? Super delocalized, you're right, Benjamin, okay? All right, let me show you, okay? So in the UV spectrometer and in the UV, okay, let me give you some theory now, okay? The theory. The theory is that, let me expand it, okay. Now follow me. In UV spectroscopy, the excitation of an electron from the lower energy ground state to high energy excited state is observed, okay? So the electrons located in the pi bond, the pi orbital, my goodness, they get excited. What kind of photons will make them excited? The UV photons, okay? All right. The transition that will be observed, okay, involved in the excitation of electron from a pi bonding, pi bonding, pi orbital, okay? And so it is the ground state like this and excited state like that. This is my ground state. This is my excited state. This is me before you play the Michael Jackson's music. This is after you play that music, I get excited like this, okay? So what kind of a music we're playing? We're playing the UV photons, am I right? Okay, all right. And so what is anti-bonding? It is just showing you I'm not the same as before. One electron is more excited than the other one. And for this reason, it does not pair up anymore. The same, it doesn't pair up the same way, understand? Okay, it does not pair up the same way as the ground state, all right? So you may say, Ms. Jean, which pi electron is capable to do that? I can tell you in that long conjugated system, any electron will be capable of doing this, okay? Yes, as long as you give them the right photon, the right energy, that photon is capable of providing the energy gap between those two levels, okay? Are you with me? Okay, all right. All right, and let me read more to you, okay? You only need to learn this paragraph today, okay? Only one paragraph, that's actually 2 half paragraph right here. The energy difference between the pi and pi star, it's a function of conjugation in the molecule. Do you hear me? This energy gap, how big that is, depending on how conjugated the molecule is. Do you hear me? Okay, the energy difference between the gap, it's a function of the degree of conjugation in the molecule. The greater the extent of the conjugation, the smaller the energy gap. Now this sentence right here is what you need to learn about today. The longer the conjugation, the smaller the energy gap. Okay? In other words, okay, if I give you, okay, a standard molecule like this, okay, this huge gap right here, okay, I can get the pi bond excited, okay. But if I increase the length of conjugation, then I can tell you this gap right here is narrow. How about narrow by 50%, depending on how conjugated it is. Understand? Okay? All right. And then what do we have to tell you? Okay. The smaller the energy difference it is, the longer the wavelength the light which is absorbed. Okay, because I know UV light carry photons and the photons carry energy. If I have an energy gap this big, okay, I need photons of some wavelengths to provide me that energy to get the pi bond excited. However, if I increase the conjugation, this gap is narrow, then it will be another wavelength of photons, another wavelength of the UV light that should be provided in order to make the bond excited. Are you with me? Okay? All right, so the smaller the energy differences, The longer the wavelength, the light will be absorbed. Okay, here, this is to tell you if I reduce the energy gap, then I will need longer wavelengths of light. Well, you remember from the past, from your general chemistry, okay? Let's take a look at some photons. How about that? The equation. Do you remember this? Have you seen this in your life? Where do you learn that from? Gen Chem. You're right. From your general chemistry, okay? So energy equals Planck constant times the frequency of the light. Okay, the light can be infrared, can be UV light, can be visible light, right? And it could be X-ray. They all have the same speed of light, same number here, the same Planck constant, but the wavelengths will be different, right? Comparing visible light to ultraviolet. Comparing ultraviolet with infrared. They all have the same speed, but the wavelengths different, okay? I want to show you, and I want to review that the photon with a large wavelength, what happened to the energy that it will provide? The photon with a long wavelength will have a small energy, am I right? The photons with a short wavelength will carry a large energy, am I right? Okay, so that energy will be used by what? By the pi electron to get excited, remember that? Okay, and this energy gap, it depends on whether this is a conjugated, very long conjugated system or a very short conjugated system. The long wavelengths will be used for a small energy gap excitation, okay? Does it make sense? Does it make sense to you, hello? All right, you may not like it, okay? Let me give you more photos. I mean slides, okay? Here. Do you see red light and blue light? Hello? Which light, which color, which photon? If I say this is my red color photon compared to the blue color photon, which one has a higher energy? Let me put it this way. Which one has a longer wavelength? Can someone respond?
Well, red has a longer wavelength.
So what happened to this energy?
It like get depleted, or is it slower? Not slower. Is it like lower?
Lower. All right, yeah. Aaron is right. I'll give you 1 point.
Oh,
Aaron says, okay, longer wavelengths. How do you know that, Aaron?
Well, just from looking at it, it seems.
You know, you're right. You can just, by looking at eyeball, right? From peak to peak, this is the wavelength of the red photon, am I right? Comparing to the blue, my goodness, peak to peak, this is wavelength. And you know, red is longer wavelength compared to the blue. And therefore, which one has more energy?
Blue.
The blue, definitely, okay? This is a very, very, very energetic photon. And I think you remember this, okay? All coming from that equation, right? the energy equals h nu. And that frequency is equal to c over lambda. C is the speed of light. And so the wavelength is inversely proportional to the energy. Am I right? Okay. The long wavelength is small energy, lower energy compared to the blue. Okay. So why is this important? Yeah, I want to show you right away. Okay. I want to talk about the gap. Okay. Ooh, not too good. Let me just enlarge it. Okay. Hey, what's going on? I don't like it. I think you're able to see this. Is it better? Kind of destructive, but I think we're fine. Oh, I can't do that. I can't expand the page, okay? I can only do this. Okay. All right. But I think you're able to handle this, okay? Now, everybody follow me. Okay, I have a pink molecule, a green molecule, and a blue. Tell me which molecule is most conjugated. Most conjugated means longest conjugation system. Conjugated the most. Let me see who gets it first, okay? The blue. Who gave me blue? Let me see. All right, Nathan gets 1 point. Okay, most conjugated. So do you remember when I was talking about the gap, when I was talking about the delocalized kid? That was me, okay? Look at this. The pi electron here, okay, can travel among 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 carbons. Am I right? Hey, the pi electron can travel, can enjoy the vacation within this territory. Ah, so much fun, huh? Yes. How about the green? The pi electron delocalize? Yeah. Travel between here, all the way to here, and all the way to here. It is. Okay, 10 plus 4, 14 carbons. It's a big home of 14 carbons. Look at the blue. Oh, I grew up this way. It is 10, 14, and 18 carbons in total. Of course, this is most conjugated. All right, now tell me, Nathan. Okay. All right, Cindy, what happened? The blue is most conjugated. Am I right? All right. And what did I tell you when I show you this chapter? I only want you to read that paragraph. Okay, the energy gap between pi and pi star is a function of the conjugation. The greater the extent of conjugation, the smaller the gap. And the longer the wavelength of light which is absorbed. Do you understand this paragraph? Okay, go back here. I know this is most conjugated, and so this is the one that has the smallest energy gap for excitation. For the pi electron to get excited, am I right? Yes. And therefore, the longest wavelength of the light it will absorb. And so let me show you, when I show you this axis right here, the y-axis is telling you, ignore this, okay? if I show you this as absorbance of the molecule, how much light it will be absorbed. The bigger peak means more absorption. And look at this x-axis from 200, 300, 400 nanometer. What is nanometer for? Hello? Lambda. What is lambda? The lambda is the wavelength, okay? It's the wavelength that will be absorbed by the molecule. So which one has the longest wavelength? I can tell you, because we all see this curve. So we want to characterize the molecule based on the wavelength that it will give you the maximum absorption. Okay, so for the blue, we call this the lambda max. It is the wavelength this molecule exhibits the maximum amount of absorption. For the green, it is this wavelength. It will enjoy maximum absorption. For the pink, it is this wavelength enjoying the maximum absorption. Okay, so this is the value we call lambda max. Are you with me? It is the lambda max between the pink, the green, and the blue. You see there is a change to energetic photon, medium energetic, and not too energetic photons. Okay, for these pi electron to get excited in the blue doesn't require much energy. Are you all with me? Okay, well, this is a fact. Okay, this is a real data. Okay, let me go back to this page one more time. So you want to continue with me reading this, okay? The wavelength of maximum absorption of light in the UV spectrum is termed the lambda max. What is lambda? Wavelength at maximum absorption. Okay? And so this is one characteristic value associated with organic substance too. If it absorbs the UV light, we want to characterize them based on this value. Okay? Okay? So I told you about this application, okay? Okay, you can characterize organic substance using this number. And look at this. Look at this. Pink and the green and the blue. Okay, doesn't require much energy to get that excited. So the blue molecule will absorb the longest wavelengths because it has the longest conjugation. So the general observation, always, the longer the conjugation, the lambda max will go to the right-hand side of the spectrum, or shift the curve, okay, to the right-hand side. The less conjugated system absorb, okay, the high energy. So tell me, in terms of eye protection, you know, that 200 area ultraviolet is really, really destructive to your eyes, okay? I can tell you this pink is really, really good protecting your eyes, right? Because it takes away the most detrimental ultraviolet photons, short wavelengths, high energy photons. Are y'all with me? So this molecule right here is more powerful, okay, taking away this, okay? I can tell you in the industry, oh my goodness, they make whole bunch. Ideally, they want the whole 200 to 400 ultraviolet range, the whole range totally blocked. This is ideal, okay? So it's a lot of thought being put into molecule design, how to get that, okay, absorption maximized for all wavelengths, okay? Are y'all good? Okay, let me show you more examples, okay? Yes, I want all of you, yeah, please echo, you know, if you are able to digest on the spot, it really help, okay? If you raise question, I will make sure to clarify, okay? All right, now this is one example. I want to show you another example. Oftentimes, you see a spectrum like this. I have a molecule like this already made. Is this conjugated? Hello? Is this conjugated? Yes. Okay. Double, single, double, single, double, single, double, single, double, all the way. So the pi electron can travel from here, 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 here. Wow. How about the nitrogen here? Oh, this is some question I will ask later. Okay. If I have a nitrogen here, what does it do to this conjugation? Okay. Okay, before we come to that, let's take a look. The spectrum. Dissolve the sample in a quartz cell. Quartz, you know what quartz is, right? Dissolve it, okay? And then use ethanol, yeah, because I know ethanol would not interfere with the signals here, okay? Dissolve it. And then we put the solution in the light path of a UV ultraviolet photons. And then we record the absorption, okay? Wow, huge peak here and there, okay? So we characterize our lambda max, maximum absorption wavelength right here, okay? At the same time, I found a smaller peak at 255 nanometer. Okay, 395 and 225. Okay, this is referring to another excitation. Okay, you don't need to know the details. You just need to know this is the true lambda, the lambda max we're interested. Okay, and if you increase the extent of conjugation, you will move this lambda max to the right hand side. The more conjugation makes the energy gap smaller and will only require photons with smaller energy to do the job, okay? To do the excitation job, okay? All right. Okay, then let me see if I have other, yeah, I think we're fine now, okay? Okay, are you all ready to go? And what I'm saying is, when I say ready to go, I want to show you the lab packet now. We can do some exercise, okay? Ready? Do you have the lab packet with you? Okay, I'll give you 1 minute. Let me get some water. I'll be right back. Get the packet ready, okay? Okie doke. Okay, mechanism and the reaction rating. This is in the book, okay? I want you to pay attention to the coefficient. I want you to know where you put the catalyst, okay? Look up the melting point. Okay, assume you get 100% yield right here. We want you to determine what is your limiting reagent, okay? Theoretical yield, yeah. Assuming 100% conversion of your product, okay? Based on the limiting reagent, what is your prediction of the yield? Okay? We have already covered this part, how many peaks you will see. Okay? Didn't I? Yeah, I think I talked about this already. Hello? So some students here in my class will be making this compound, okay? Some will have a longer conjugation system. Some will have a substituents on the ring, okay? Regardless, this is the baseline of your the ALDOL product, okay? The basic structure of the ALDOL product. We want you to review your NMR. If I take an NMR, carbon 13, you want to help me identify which carbon will be most deshielded, okay? I can tell you this is actually based on your common sense. How about this one? You need to look up, okay? It's in the textbook, or go ahead and Google it. You'll find it, okay? All right, here comes the real question. Based on this, we have so many questions. So 1, 2, 3, 4, 5 total, all right? All right, ladies and gentlemen, look at the question. By adding one single para dimethyl amino group to the aromatic ring, I only want one, okay? One single para means right here. Dimethyl amino group, how does it look like? It looks like this, right? Is this in the para position? Is this the dimethyl amino group? Yeah, this is it, okay? Okay, and what else? Draw the molecular structure and show what may happen to the conjugation system. Aha. I'm saying if you introduce a para-dimethyl amino group right here, something will happen to the conjugated system. Okay? I want to ask you, is this conjugation extended or shortened? So just get to the point. Tell me, is this extended or shortened? You have to draw that molecule first, okay? With the dimethyl amino group attached at the para position. This is where my little hand is located. And show me what will happen to the conjugated system. I want to alert you, the lone pairs are very important, okay? You learned that from the aromatic ring chapter. You learned that from your nitration chapter. And I just want to give you a hint, okay? You go ahead and figure out, okay? Are you able to follow my hint? Can you respond?
Yes, we can see the hand.
Okay. Lazo. Wow. Lazo is thinking at the speed of light. And I cannot answer your question, okay? Because I cannot announce the answer, okay? But I have to say, yeah, Lazo, you're thinking along the right track, okay? Okay, all right, next. So we want you to think whether it's going to be extended or shortened, okay? And so from this question right here, okay, now this molecule already extended, I mean, would you already attach this nitrogen and then methyl group? So whatever you do to the conjugation, what do you expect the lambda max value will be? Is it going to be longer wavelength or the shorter wavelength, okay? Do you understand the question now? Okay. Once you attach that substituent right here, you would do something about this conjugation, okay? And so whether it is shortened or extended, in the extended conjugation, it will change the lambda max compared to the original, okay? And we want you to compare that with the original 2A. It is the molecule of this, okay? All right, next. The molecule from this newly attached group, okay, added to the ring, okay? The molecule 3A, and I add HCl to it. We want you to draw the molecule. What happened when you add HCl? And what does it mean to the conjugated system then? Okay, the whole thing is asking you to see if the conjugation get extended or shortened, okay? Or by adding the acid, you can also cause some change to the conjugation too, okay? And so let me tell you, this chapter, I think I spent almost 1 hour talking about this. This chapter is also in your green connection, the green connection book, okay? That green connection book. Okay, I need to give Lazo a point. Okay, so today only 3 students got the point. I'm not happy. I think I want to offer more opportunity. So look again. Okay. We're attaching such a group onto the ring. Just by looking at this aldehyde, okay? Without this whole substituents, it has conjugation already. It will be very similar question to the one written in the packet. I attached this ring to the ring, this substituents. Okay, by adding this nitrogen and then methyl group, you can do something about the ring. Okay, you can do something about the ring. Remember, the electron density can be increased or decreased, am I right? From your nitration chapter, or we call the the electrophilic substitution mechanism, the SE mechanism, when you learn about the nitration, okay? And so help me. With this substituent here, are you making the ring more electron rich or electron poor? Can someone answer that question? Bonus. Think about resonance, okay? Think about the resonance. Is anyone writing here? No. Anyway, this is the maximum amount of hint I can provide to you, okay? With this substituents, okay, there's something about this group that can change the conjugation of the ring, okay? And when you add HCl to it, I want you to know, at least can you respond? Hello? Do you think the hydrochloric acid can react with the molecule of 3A? Now someone says, electron poor or electron rich? Cindy, you're right. Cindy gets 1 point, okay? And I want all of you, yes, to look. Okay, now Megan offer more answers. Electron rich because the group is electron donating electron density into the ring. Yes. Megan even, yes. Very, very clear about her message. Yes. Actually, with the nitrogen next to the ring, yeah, that nitrogen will do. What is noise? Okay. You're right, Megan. The electron density will increase because of nitrogen, okay? Okay, so can you write about that then? What does it mean to the conjugation then? Okay? I think this is all in that chapter, in the nitration chapter, okay? Anyone here has a question? Nathan, I don't quite get your comment here. Noise. What is noise? Are you hearing it? Oh, nice. Okay. Okay. I thought there's some background noise from my end. No. My house is really, really quiet. Okay. I'm happy. Now 5 students got the bonus point. So I want you to tell me any question you may have. Are you able to turn in this worksheet tomorrow? And a day after today? 24 hours? Hey, who's this? Yes, okay. Probably sooner. Yeah, good for you, Benjamin. Get it done, okay? And so next week, I will go over the potential mistakes, okay? Not the potential, the mistakes I spot on the grading part. Okay, I'll go over the common mistakes, okay? Next week, I will take only go over the mistakes, and then I'll take questions, and if not, then I'll say adios until final exam. I will give everybody announcement on Beachboard, okay, how you prepare for the final. And by the way, you already know how to prepare for final, okay? The final exam, I think I said this very many times, you want to keep the worksheet. And because a lot of questions actually come out of the work packet, okay? We modify it, and then it will be just like 223A. Okay, we modify the questions, we change the molecule, and then we give you spectra, etc. And yeah, and this is going to be online also, okay? But the problem is, students, you have to understand, when you do multiple choice, questions from multiple choice, you don't get partial credit. If you pick the wrong answer, then you're dead wrong. You know what I mean? We don't care about your partial knowledge there, okay? So when you prepare for the final, look at all the mistakes I was talking about and make sure you know everything about the mistake you made, okay? Okay, so Megan asked me, I didn't catch it. Did I get a point? Yeah, Megan, you got a point, no problem, yeah. Cindy gets also 1 point, yeah. Okay? It's very nice. Okay, every point you pick up here is the same as the point you get from the exam, okay? It's the same. Every point weighed the same as the report, everything, okay? It's all equal, okay? It's really, really good. When I started this policy of bonus point opportunity, when I challenge people to think about the answer, when I provide the hint, I realize people are able to grow much better. Okay, so it's really good. Okay, are we going to get a grade update before the exam? Definitely, okay? I should be able to finish your ALDOL report before we get together next Thursday. So I will talk about your mistake, okay? And that will be our last Zoom lecture, okay? That will be our last Zoom lecture, but I will always take questions from email. If you do have questions, please write me email and check Beach Board announcement regularly. Okay, so how can you Zoom with me individually? Did I give you my private meeting ID number? If not, I'll post it on Beach Board. Okay, Amanda and everyone. Okay, I will post, I will post my private meeting ID number right after this class is dismissed. Okay, so just in case you have any concern about your oh, Miss Jean, I think I did better in that report. I really want to go through my mistakes. Yes, please set up an appointment with me. The best time to do this Zoom private meeting, I would say right after the class, okay? Right after the class, okay? Okay, so send me email. You know how often I check email? I'll say 6 times a day, okay? At least 6 times a day, okay? And if I don't reply to you, I can tell you there are a couple scenarios, especially when people try to send me email from their own private email address. I think for some reason the school will block it, okay? Or they will consider that as a scam. Or if it is a large attachment there, then definitely we'll put in the trash automatically. We don't know why, okay? And I noticed this problem for a long time actually. And just recently, because I teach other classes, the higher level, the 400 level, my goodness, students were saying, Ms. Jean, you didn't reply to my email on this date. And then when I opened my email, I realized it's in the trash, in the scam, sorry, in the scam. So I just have to alert you, okay? Oftentimes, yeah, such a problem do happen. Okay. And so Cindy, I'll look forward to have a private meeting. Okay, and you're all welcome. Okay, and I will take care of the question one after one. Okay. before I say goodbye, is there another question? Hello? A lot of you are so quiet today. Oh, it's probably because you decide to mute your microphone. So are we okay now? You all able to handle your work packet, right? Yes, I have that confidence, okay? All right, I'll see you next week, okay? Bye-bye.
Thanks, Dr. Jean.
Bye-bye, have a good one.